Hi everybody, thank you for attending my presentation. I am Yinan Liu from Nankai University. Firstly, let's look at the title of our paper. In this paper, we explore a new task of joint open knowledge base canonicalization and linking. Okay, let's begin to introduce the paper. First, let's talk about the motivation. In recent years, several large curated knowledge bases with an ontology of pre-specified categories and relations have been developed, such as Freebase, DBpedia, and Yago. In these CKBs, each entity is canonicalized and well-defined with a unique identifier. CKBs play a key role for a variety of applications in both industry and academic. However, they are far from complete. Enriching existing CKBs with external resources becomes more and more important. Open information extraction methods without any pre-specified ontology can extract OIE triples of the form name phrase, relation phrase, name phrase from unstructured text documents. This large number of OIE triples compose large open knowledge bases, such as Reverb, TextRunner, and OLIA. Unlike most CKBs confined to some encyclopedic knowledge sources, for example Wikipedia, the advantage of OKBs is that the coverage and diversity are much higher. However, compared with CKBs, OKBs are noisier and often plagued with ambiguity due to the lack of unique identifiers for the name phrases and relation phrases in OIE triples. As the example shown as follows, we list three OIE triples of an OKB. It can be seen that University of Maryland S1 and UMD S2, which are two name phrases from different OIE triples, and be a member of P2 and be an early member of P3 are two relation phrases from different OIE triples with the same semantic meaning. To eliminate the ambiguity in OKBs and enrich CKBs with OIE triples, OKB canonicalization and OKB linking are two important tasks that need to be solved urgently. OKB canonicalization is the task of converting OIE triples to canonicalized form, where name phrases or relation phrases with the same semantic meaning are clustered to a group. Some models based on string similarity and embedding techniques have been proposed to canonicalize OKBs. A recent work achieved better performance by leveraging set information from the original source text. OKB linking is the task to jointly link name phrases and relation phrases in OIE triples with their corresponding real-world entities and relations in a CKB. A recent work has been published on VLDB. In fact, OKB canonicalization and OKB linking are tightly coupled, and one task can benefit significantly from the kind of information provided by the other. Next, I will give the definition of our task. Given a set of OIE triples in an OKB and a CKB, the target of this joint task is to cluster NPs or RPs with the same semantic meaning into a group. That is OKB canonicalization. And meanwhile, linking each group of NPs or RPs with their corresponding real-world entity or relation in a CKB, that is OKB linking jointly. For illustration, we show a running example of this task in this figure. The input is three OIE triples and a CKB. With respect to the canonicalization result, marked with blue ellipses, we should cluster NPs into 4 groups and cluster RPs into 2 groups. With respect to the linking result, marked with blue arrows, we should link each group of NPs or RPs with their corresponding entity or relation in the CKB. We list the challenge of our task as follows. How to make these two tasks reinforce each other. How to make use of all useful signals from both tasks. How to make the framework flexible and able to extend to fit new signals of both tasks. Next, I will introduce our framework Joko. Given a set of OIE triples in an OKB as well as a CKB, our framework firstly constructs a vector graph for each task respectively. With respect to the task of OKB canonicalization, Joko generates a variable node for each pair of non or relation phrases to represent whether they have the same semantic meaning, and adds OKB canonicalization signals and transitive relation signals as vector nodes. With respect to the task of OKB linking, Joko generates a variable node for each non or relation phrase to represent its corresponding entity or relation in the CKB, and adds OKB linking signals as fact inclusion signals as vector nodes. Subsequently, in order to make these two tasks reinforce each other, consistency signals are added as vector nodes to perform the interaction between two tasks. Sij, Pij, and Oij, called subject, predicate, and object pair variables, are used to represent the NP pair SISJ, the RP pair PIPJ, and the NP pair OIOJ respectively. Xij, Yij, and Zij, called subject, predicate, and object canonicalization variables, corresponding to the variables Sij, Pij, and Oij respectively. The canonicalization variable represents whether two NPs or RPs have the same semantic meaning. We utilize some NP canonicalization signals to define F1 or F3 as a vector function over subject or object pair variable and its corresponding subject or object canonicalization variable. IDF token overlap is based on the assumption that two NPs sharing infrequent words are more likely to refer to the same object in the word. We use the cosine similarity to calculate the similarity between the embeddings of two NPs. If two NPs have the same cluster representative, according to the index based on PPDB, they are considered to be equivalent. We utilize some RP canonicalization signals to define F2 as a vector function over a predicate pair variable and its corresponding relation canonicalization variable. Apart from IDF token overlap over word embedding and PPTB, we use the following two additional signals. ARMY algorithm can judge whether two RPs represent the same semantic meaning by learning Hall rules. Stanford knowledge-based population system can link a RP to a relation in a CKB. We utilize transitive relation signals to define a vector function U1, U2, and U3 over 3 subject relation and object canonicalization variables that satisfy transitive relations. As an example, if values of this kind of 3 canonicalization variables satisfy transitive relation as follows, they should be rewarded. If their values violate transitive relations, they should be penalized. Si, Pi, and Oi called subject variable, predicate variable, and object variable represent NP, RP, and NP of an OIE triple respectively. ESI, RPI, and EOI called subject, predicate, and object linking variables corresponding to the observed variables Si, Pi, and Oi respectively. ESI or I represents the semantically corresponding entity or relation existing in the CKB for Si or Pi. We utilize some OKB entity linking signals to define F4 or F6 as a vector function over a subject or object variable and its corresponding subject or object linking variable. Apart from word embedding and PPDB, we utilize the entity popularity to denote the prior probability of the appearance of a candidate entity given an entity mention. We utilize some OKB relation linking signals to define F5 as a factor function over a predicate variable and its corresponding predicate linking variable. Apart from word embedding and PPDB, we also use ngRIM and LD as other two OKB relation linking signals. We utilize fact inclusion signals to define a factor function U4 over a subject linking variable, a predicate linking variable, and an object linking variable that correspond to the same OIE triple. Specifically, we define a fact inclusion feature function over three linking variables. If values of linking variables with respect to an OIE triple compose a triple already included in a CKB, they should be rewarded. OKB canonicalization result and OKB linking result should be consistent. We utilize consistency signals to define a factor function U5, U6, and U7 over a subject predicate and object canonicalization variable and its corresponding to subject predicate and object linking variables. For example, if values of these corresponding variables satisfy consistency relations, they should be rewarded, otherwise they should be penalized. Now, we introduced the learning and inference algorithm of our framework. For our model, the factor function of any factor node can be represented in a unified form as follows. We could use the product of these factor functions to represent the joint probability over variables as follows. And we rewrite this function as follows. Finally, we can obtain the log likelihood objective function and the gradient for parameters omega can be calculated as follows. Specifically, we define a reasonable working procedure for the LBP algorithm based on the structural characteristics of our vector graph. After we learn the optimal parameters, we can infer the best label of each variable with final message. To eliminate conflicts between the results of OKB canonicalization and OKB linking, we design an intuitive method to generate the final result. If a pair of NPs are located in two different groups, according to the linking result and the corresponding canonicalization variable of this pair has a value of 1, we select the label of the larger group as the final label for both NPs. Two large-scale available OIE triple datasets are used in the experiments. For the task of OKB canonicalization, we adopt the same evaluation measures as previous works. To give an overall evaluation, we calculate average F1 as the average of macro F1, and pairwise F1. For the task of OKB linking, we adopt accuracy. From the results shown in these tables, we can see that Joko outperforms all the baselines in terms of average F1 for the task of OKB canonicalization. From the results, we can see that Joko outperforms all the baselines in terms of accuracy for the task of OKB linking. We present the performance of two variants, namely Joko-Cano and Joko-Link, as well as the whole framework in this table. From the experimental results, we can see that Joko outperforms Joko-Cano and Joko-Link in terms of average F1 accuracy over OKB canonicalization and linking task, which demonstrates that the whole framework Joko could indeed perform the interaction between two tasks effectively and make them reinforce each other obviously. We define three different variants of our framework Joko shown in this table by leveraging different combinations of the feature functions for each factor function in the factor graph. From the experimental results, we can see that Joko O achieves the best performance for both tasks. The more useful signals, the better the performance, which is consistent with our intuition. Now, I will give a conclusion of my paper. First, we are the first to explore the new joint task. Second, we propose a novel framework Joko to perform OKB canonicalization and linking jointly, and make them reinforce each other. Joko is flexible enough to combine different signals from two tasks together, and able to extend to fit any new signals of both tasks based on factor graph model. Finally, a thorough experimental study over two real-world datasets shows that Joko outperforms all the baseline methods for both tasks in terms of average F1 and accuracy. Okay, that's all. Thanks.